So section 7.1 is more of a review of your logarithmic and exponential functions. If you feel really confident of all the properties and derivatives and integrals and everything, you can move through this pretty quickly and just try the homework and see how you do. But if you need it, this is a nice little review for you. So if you recall your basic logs, and we tend to work with E and ln so much, I want to also go back to the basic log log, which is essentially, right, another way of writing an exponential. So remember, when you write a log, the base is what gets put here. That's your C, and it's your exponent that's kind of sits out there on its own. So a to the b equals c, log a c. I think there we go. What I did in school was kind of learn that circle the a to the b to the c. So a to the b equals c. Anyway, some very common ones to remember is if you have log base 10, it's just called log. All right. When you have a base 10, we don't actually use, when you don't see that base, it's assumed to be 10. And of course, if you have a log base E, that's where you have ln. Sorry, we'll put the x in there. It makes it a little more interesting, right? Log base E of x is just ln of x. Also, some really common things to remember that's going to help you a lot. Log of anything of 1 is second you have a 1 in that position, what you're asking is, what do I have to raise a base to for it to equal 1? What is the only exponent that gets you a 1? And that, of course, is 0. So that means ln of 1 equals 0. Okay, a lot of these, they come up a lot, so please make sure you know them. Another one that comes up a lot, if you see it in the log, what if I want to take my base to the same number? You're saying, hey, what do I raise my base to keep it my base and not have it change? Well, then it's being raised to a 1. And with the natural log, of course, that would be the natural log of E. Since E is the base, to keep it E, you raise it to the first power. So please make sure you keep those in mind and don't forget those common. As we're going to see in the next section, we do some more application problems. You know, the logs work great to help us take any type of exponential type problem, especially when we have variables in the exponents, to change it. You may have recall in school saying, hey, let me just take ln of both sides, right? Let me just take ln of both sides. Well, that's great, except you have that little issue with the 3. So before we do that, let me put my problem back. Let's just get the exponential on its own. And that's like a common mistake students make, is not to get that exponential function by itself, and you can just do 17 divided by 3. Okay? And then sure, you can just do ln of both sides. You might have learned this where the ln and e cancel each other out, and I'm left with 6x equals ln. Or you don't even have to do that. You can look at the original problem and just say, hey, wait a minute. Let me reconvert it using this idea here, right? So again, I get it to e to the 6x equals 17. No matter what you do, it's always best to get that exponential completely on its own. So divide out any coefficients it has, and then that's just, ln base e, 17, forgot the thirds, equals 6x. So however you want to do it. And then from there you can easily solve the problem because you can stick in ln 17/3 into your calculator and divide by 6. So we will, hopefully you remember some of your basic exponential equations. Here's a kind of more formal definition of ln x, and that's saying that ln x equals the integral from 1 to x 1 over t dt. Don't worry that I'm using t, it's just a placeholder. I could use ds, 1 over s ds, 1 over r dr, doesn't matter. I'm like, why would you do that? Well, it just keeps it, well, here, let's just prove to make sure it works, right? The integral, right, of 1 to x, 1 over t dt, well, that's just going to be ln t, because differentiating with respect to t, from 1 to x, well, isn't that just ln x minus ln 1? So, yeah, it's ln x. So, yeah, it works. And again, you can see right away, the t was just a placeholder. It doesn't matter what letter I stick there. Why is this definition important? Well, normally, we have to work with the absolute value of x. What this definition does is it takes away saying, well, we're going to just start at 1 and go to anything. And we can, x is, since 1 is our lower limit, x is our upper limit, we can clearly, it's going to be positive. So don't have to worry about that, the absolute value. A couple reminders when dealing with ln x, of course. Now, ddx of ln x is, of course, you can see it there, the opposite of that. It's going to be 1 over x, right? Well, I can generalize that, and I want you to stop thinking, because we never, ever come across just ln x. Normally, we come across ln of a function, and we have to use the chain rule. And hopefully you've done that enough that you're almost making this shortcut on your own. So let's do a general definition for ln of a function, right? Well, think about it. Whatever f of x is, that goes in the denominator. And what goes in the numerator? Using chain rule, isn't it simply the derivative of f of x? So we can kind of generalize our ln derivative to this. And then you're not constantly thinking about the having to work out the chain rule. It's there and done for you. Then we can generalize it even further, because ln is a very specific type of log. So do you recall how you do d, one second, d dx of log base x? So now I'm taking a look at, let me get rid of this off to the side here, taking a look at a more general log function. So if you recall, it is 1 over x times the natural log of b. Right? And this makes sense because when log was just an ln, meaning the base is e, right? ln of e is just 1, so that's why this particular one over here just comes out to 1 over x, because it's technically 1 over . So, of course, we have 1 over that function. But where I have a 1 in the numerator, I have a 1 in the numerator because the chain rule, the derivative of x is just 1. But because we're going to need to use a chain rule, we need to have f prime of x up here. and our ln of whatever our base is. And that is a much more generalized derivative of any type of log function. Now we can kind of move on also to just quick review of our exponential function, which is of course the inverse of ln. And our exponential function always, any base, no matter what it is, when you raise it to the 0 power, it's a 1. It's going to slowly decrease as you go to negative infinity, and then it's going to increase as you go to positive infinity. And this is just what the general graph of y equals b to the x is. If it was y equals e to the x, it kind of looks like that. Depending on what the base is, just says how wide your function ends up being. But it approaches 0 as it goes to negative infinity, approaches infinity as you go to infinity, and it is always has a point at 0, 1. And of course, we can do, you know, if we make it the more general e to the x, we have something very popular called our exponential growth function. Y equals e to the x. And then y equals e to the negative x is going to be a similar function, just going in the opposite direction, right? Now we're heading 0 as x approaches infinity, but we don't have a limit. It's just positive infinity as x approaches negative infinity, and this is still the point 0, 1. This one is your classic exponential decay function, which will come up in the next section where we talk about exponential growth and exponential decay. And of course, your derivative, right? You all know dx of e to the x is simply e to the x. We can generalize that to a function, and using the chain rule, it's going to be e to that function times the derivative of that function. And then, of course, we can generalize it over here to any base, which was b to the x ln b. Again, that's if you put ln e here, ln e comes to 1. That's why we do not need to include it. But we do need to include it when e is no longer the base. And then we can take this one step further and generalize it to, sorry, I don't know why I wrote equal signs there. It's parentheses, I apologize. And generalize b to any function equals b to that function times, here's where the chain rule comes in, and then of course your ln b. That is the most general. From any of these, of course, you can get your integral functions. Do recall, which is going to come in handy, we'll go over them very briefly, and they are your properties of logs. So we'll use the natural log to do them, but the same properties apply. To when it's not the natural log and you have various bases. So the first, ln of xy, remember this, is ln x plus ln y. Ln of x divided by y is ln x minus ln y. If you recall, in Calc 1 we did logarithmic differentiation, touched upon it, and you were able to expand a function using the properties of logs to make it a little bit easier to differentiate it. Ln of x to some power, you move the power out front, and you have ln x. To continue, let's look at e. Well, e to the x plus y. So here's an interesting one if you think about it. Isn't that just e to the x times e to the y? Because if you have the same base, you add your exponent. So that's a way to think about separating or combining. In the same way, e to the x minus y is e to the x over e to the y. E to the x p is e to the x raised to the p power, and vice versa. A couple other properties to think about. Ln of e to the x. Well, that's just going to be x. Another one, e to the ln x. Well, that also is just going to be x. Ln and e have these kind of cool properties that you need to remember. That is pretty much all I wanted to do for a quick review of exponents. So a nice short video.